Look up tonight. If the skies are clear, you'll probably see it, that pale silver disk hanging above you, like it's always been there, like it will always be there. We barely think about it. We barely notice it anymore. It's just the moon. But what if it was gone? Not moved, not dimmed, gone, erased from the night sky and from every chapter of history that came before this moment. The world you would wake up to would not simply be darker. It would be different times, in ways so fundamental, so deeply woven into the fabric of life on this planet that you might not recognize it as Earth at all. This is the story of our moon, what it gave us, what it still gives us, and the strange, violent, beautiful world we would have inherited without it. Number intro plus subscribe prompt 040 115 Co. A. Tidal card. What if Earth had no moon? Bold white text against a star field with a conspicuous dark circle where the moon should glow. Narrator VO. Welcome. If you're the kind of person who lies awake at night wondering about the universe, about what might have been, what could still be, and what invisible forces are holding your world together right now, then you are in exactly the right place. Today, we're going on a journey. We're going to dismantle the Earth as we know it, remove one of its most ancient companions, and rebuild it from scratch, scientifically, ecologically, and historically. By the end of this video, you will never look at the moon the same way again. If you enjoy exploring the deep questions of our cosmos, please take a second to like this video and subscribe to the channel. It genuinely helps us keep making content like this, and there is so much more coming. Now let's go back to the very beginning. Section 1. The moon's origin and its role. Today, 1:15:12. Visual. A swirling protoplanetary disk, hot gas and rock, spiraling around a young, furious Sunday. The solar system is a construction site, chaotic, violent, still becoming itself. Narrator VO. To understand what we lose without the moon, we first have to understand how we got it, and the answer, when you really sit with it, is almost unbelievably violent. About 4.5 billion years ago, our solar system was young and absolutely chaotic. The planets hadn't settled into the orderly orbits we know today. They were jostling, drifting, occasionally catastrophically colliding, and early Earth, a molten, half-formed world not yet recognizable as home, was right in the middle of all of it. Then, sometime around 4.5 billion years ago, something hit us. Not a rock, not an asteroid, a times planet. Scientists call it Theia, a Mars-sized body that had been forming in roughly the same orbital zone as early Earth. Some models suggest it sideswiped us at a shallow angle, like a billiard ball caught on the edge of another. Others suggest it was more of a head-on graze. Either way, the impact was so catastrophically energetic that the outer layers of both bodies were vaporized and flung into space in a roiling, incandescent cloud of rock vapor and molten debris. Visual. A slow-motion simulation of the impact Earth glowing like a lava lamp hit by a wrecking ball, a spray of superheated matter arcing into orbit. For perhaps 1,000 years, maybe more, Earth was surrounded by a disk O. Look up tonight. If the skies are clear, you'll probably see it, that pale silver disk hanging above you, like it's always been there, like it will always be there. We barely think about it. We barely notice it anymore. It's just us, the moon. But what if it was gone? Not moved, not dimmed, gone. Erased from the night sky and from every chapter of history that came before this moment. The world you would wake up to would not simply be darker, it would be different in ways so fundamental, so deeply woven into the fabric of life on this planet that you might not recognize it as Earth at all. This is the story of our moon, what it gave us, what it still gives us, and the strange, violent, beautiful world we would have inherited without it. Welcome. If you're the kind of person who lies awake at night wondering about the universe, about what might have been, what could still be, and what invisible forces are holding your world together right now, then you are in exactly the right place. Today we're going on a journey. We're going to dismantle the Earth as we know it, remove one of its most ancient companions, and rebuild it from scratch, scientifically, ecologically, and historically. By the end of this video, you will never look at the moon the same way again. If you enjoy exploring the deep questions of our cosmos, please take a second to like this video and subscribe to the channel. It genuinely helps us keep making content like this, and there is so much more coming. Now, let's go back to the very beginning. To understand what we lose without the moon, we first have to understand how we got it. And the answer, when you really sit with it, is almost unbelievably violent. About 4.5 billion years ago, our solar system was young and absolutely chaotic. The planets hadn't settled into the orderly orbits we know today. They were jostling, drifting, occasionally catastrophically colliding. And early Earth, a molten, half-formed world, not yet recognizable as home, was right in the middle of all of it. Then, sometime around 4.5 billion years ago, something hit us. Not a rock, not an asteroid, a times planet. Scientists call it Theia, a Mars-sized body that had been forming in roughly the same orbital zone as early Earth. Some models suggest it sideswiped us at a shallow angle, like a billiard ball caught on the edge of another. Others suggest it was more of a head-on graze. Either way, the impact was so catastrophically energetic that the outer layers of both bodies were vaporized and flung into space in a roiling, incandescent cloud of rock vapor and molten debris. For perhaps 1,000 years, maybe more, Earth was surrounded by a disk of vaporized rock. And from that disk, gravity did what gravity always does. It pulled, it gathered, it collected. And piece by piece, the rubble coalesced into the moon. This is called the giant impact hypothesis. And while it sounds almost mythological, the evidence is remarkably strong. The moon's composition is extraordinarily similar to Earth's mantle. There's almost no iron in it because the iron had already sunk to Earth's core before the impact. And the lunar rocks brought back by Apollo astronauts carry chemical signatures that place their origin right here, in our own world's ancient crust. We didn't just find a moon, we made times one out of catastrophe. But here is where the story gets interesting, because from the moment the moon formed, it began doing things that would turn out to matter enormously. Time lapse of the moon slowly pulling away from Earth over geological time. In the early solar system, the moon was 3 to 5 times closer than it is today, a monstrous, luminous disk hanging low in the sky. When the moon first solidified from that debris cloud, it was much, much closer to Earth than it is today. Some estimates put it as close as 20,000 kilometers away, compared to the roughly 384,000 kilometers it sits at now. Imagine a full moon that filled not a small coin held at arm's length, but something closer to a dinner plate. It would have blazed in the sky with a ferocity that makes today's moonlight look like a candle in a stadium. And over billions of years, the gravitational interaction between Earth and the moon has been slowly, incrementally pushing the moon outward. It retreats by about 3.8 centimeters per year, roughly the rate at which your fingernails grow. It doesn't sound like much, but over 4 billion years, that small annual retreat adds up to a massive change in the moon's position. This retreat is directly linked to one of the moon's most important jobs: slowing Earth's rotation. Early Earth spun extraordinarily fast. A day on the young Earth may have been only 6 to 8 hours long. The moon's gravitational pull has been acting like a brake on Earth's rotation ever since, gradually stretching our days, slowing our spin, stabilizing our world. The same gravitational energy that is nudging the moon outward is sapping the rotational energy of Earth, giving us our familiar 2-4-hour day. Without the moon, Earth might still be spinning at something close to that original, frantic pace. But the moon doesn't just slow us down, it steadies us. Earth's axis is tilted at about 23.5 degrees relative to its orbit around the Sunday. That tilt is why we have seasons, why summers are warm and winters are cold, why some days are long and some are short. It is the metronome of our climate, the heartbeat of our agricultural calendar, the organizing principle of almost every ecosystem on Earth. And the moon keeps that tilt stable. Without the moon's gravitational steadying influence, Earth's axial tilt would not sit quietly at 23.5 degrees. It would wander chaotically. Over millions of years, it could swing from nearly 0 degrees, essentially no tilt, no seasons, to perhaps 85 degrees, where Earth would be rolling on its side like a barrel, with the poles alternately baking in months of continuous sunlight and freezing in months of utter darkness. We know this happens. It happens on Mars, which has no large moon. Mars's axial tilt has swung from about 10 degrees to as much as 60 degrees over its history, and scientists believe this has contributed to Mars's inability to maintain stable liquid water at the surface. Its climate has lurched. Its habitability has been intermittent and unreliable. The moon is our axis stabilizer, our cosmic gyroscope. It holds us in place so that climate operates within a narrow enough band for complex life to persist, for ecosystems to develop over billions of years without being periodically wiped out by a planet that suddenly decides to tilt itself into a new catastrophe. Those are the moon's 2 biggest structural contributions, giving us our day length and keeping our tilt stable. But the moon does something else that touches every living thing on this planet every single day, and we'll get to that in just a moment. Let's do the thought experiment properly. Let's take the moon away, not slowly, not gradually, but completely, gone, as if it had never formed. What does Earth look like? The first thing you would notice, if you could observe from space, is that Earth is spinning faster, much faster. Without the moon's gravitational braking, Earth retains its primordial spin rate, Depending on exactly how fast early Earth rotated, a day might be somewhere between 6 and 10 hours long. The planet is whipping around its axis at roughly 2 to 3 times the current rate, and that has consequences that cascade through everything. A faster spinning Earth generates a more powerful Coriolis effect, the phenomenon that makes winds and ocean currents curve as the planet rotates beneath them. On a fast-spinning Earth, the Coriolis effect would be dramatically amplified. Weather systems would be more extreme, more energetic, and organized differently. The bands of high and low pressure that drive our planet's climate would be narrower and more intense. Storms would form faster and dissipate faster. The atmosphere itself would behave almost like a different substance. Think of it this way. Imagine stirring a cup of coffee. The faster you stir, the more vigorous the circular patterns become, the more the liquid seems almost alive with energy. Now scale that up to a planetary atmosphere. A faster rotation means more vigorous circulation. More vigorous circulation means more powerful, more persistent winds, and likely more extreme weather. There is a concept in atmospheric science called the Rossby number, which describes the balance between inertial forces and the Coriolis effect in a rotating fluid system. At higher rotation rates, the Coriolis effect dominates more strongly, and weather systems tend to become elongated along lines of latitude rather than developing as the big, circular cyclones and anticyclones we're familiar with. Our weather would be strange, alien almost. But that's just the atmosphere. What about the surface? Without the moon slowing Earth's rotation, and without the moon pulling on our oceans, the oceans themselves would redistribute. A faster spin means Earth's equatorial bulge would be more pronounced. Centrifugal effects would push more water toward the equatorial regions. The polar oceans might be somewhat shallower. The equatorial oceans might be deeper and somewhat more expansive. Coastlines around the tropics might be different, lower lying, more frequently inundated. The continents themselves would be roughly the same shape and position. Plate tectonics, the great engine that moves continents, builds mountains, triggers earthquakes, and drives the volcanic activity that regulates our atmosphere, operates on heat from Earth's interior. The moon has virtually nothing to do with it, so Eurasia is still where it is. Africa is still where it is. The Himalayas still rise where they always have. But the world on top of those continents? That's where things get strange. Without the moon, our nights are different, radically different. On a clear night today, a full moon provides enough light to cast shadows, to read by, if you're committed, to navigate by with ease. That light has shaped millions of years of biological behavior. Nocturnal animals evolved their strategies partly in response to moonlight cycles. Predators learned to hunt on dark nights. Prey animals learned to hide. Creatures learn to judge the moon's phase and orient their lives around it. Without the moon, the night belongs entirely to the stars. The sky would be, in some ways, more spectacular. No lunar glare washing out the fainter stars. But it would also be functionally, impenetrably dark on cloudy nights. The concept of navigating by moonlight, something humans relied on for hundreds of thousands of years, would simply not exist. And here is a thought worth sitting with for a moment. In a moonless world, the night sky would be so consistently, profoundly dark that the stars would be the dominant visual experience, of every clear night. Entire civilizations might have developed astronomy and celestial navigation much earlier, driven by necessity, because the moon wouldn't be there to make nighttime navigation easier. Or conversely, the radical darkness of nights might have made human beings far more conservative, far more reluctant to travel after dark, which would have shaped the geography of early settlements, trade routes, and civilization in ways we can barely imagine. But before we get to civilization, we need to talk about what the removal of the moon does to the thing that covers most of Earth's surface: tides. We take them so much for granted that most of us, even those who live on coastlines, barely think about them. They are just the breathing of the sea in and out, twice a day, reliably, endlessly. But they are not random. They are not arbitrary. They are the direct mechanical consequence of the moon's gravity reaching across nearly 400,000 kilometers of space and literally pulling the oceans out of shape. Here is how it works. The moon's gravity pulls on every part of Earth, but it pulls harder on the side of Earth facing the moon and weaker on the far side. This creates a stretching effect. The oceans on the moon-facing side bulge outward toward it, and interestingly, the oceans on the opposite side of Earth also bulge outward, not toward the moon, but away from it, because they're on the lagging side of the gravitational gradient. As Earth rotates beneath these two bulges, any given coastline passes through them twice a day, producing 2 high tides and 2 low tides every 24 hours. The sun also pulls on Earth's oceans, but it is so much farther away that its tidal force is only about 46% as strong as the moon's. When the sun and moon align at new moon and full moon, their tidal forces add together, producing the higher, lower spring tides. When they're at right angles, their forces partially cancel, producing the gentler neap tides. Now, remove the moon. Without the moon, tides don't disappear entirely. The sun would still produce tides, but they would be less than half the strength of our current tides, and they would operate on a different rhythm, once a day rather than twice, following the sun's position rather than the moon's more complex orbital cycle. The tidal range, the difference between high and low tide, would collapse dramatically. In places like the Bay of Fundy in Canada, where the tidal range currently reaches 16 meters, the highest in the world, you might be looking at ranges of just a few meters or less. In most places, what we call tides would be so subtle as to be nearly imperceptible. The sea would rise and fall by inches rather than feet. This sounds like a minor inconvenience. It is not. It is a civilizational and evolutionary catastrophe. Consider first what tides do for coastal ecosystems. The intertidal zone, that band of coast that is alternately submerged and exposed twice a day, is one of the most biologically productive and ecologically important habitats on Earth. It is a zone of extraordinary stress and extraordinary abundance. The organisms that live there have evolved to withstand both immersion and exposure, both flooding and drying, both predation from sea creatures when the tide is in and predation from land creatures when the tide is out. This constant challenge has driven an evolutionary arms race for hundreds of millions of years, producing some of the most specialized, resilient, biochemically inventive organisms on the planet. Intertidal zones are also nurseries. Many fish species breed in coastal shallows and tide pools. The churning of tides mixes nutrients from the deep ocean into shallow coastal waters, fertilizing the explosive productivity that makes coastal fisheries so abundant. Remove strong tides, and you remove this mixing engine. Coastal waters become more stratified, more nutrient-poor, more stagnant in some respects. The intertidal zone as we know it would not exist without strong tides. The extraordinary biodiversity it supports, the barnacles and mussels and sea stars and anemones and crabs and hundreds of species of fish and invertebrate, would be reorganized, diminished, or gone. The coastline would be, by comparison, ecologically thin, but there is something even larger at stake here than coastal ecosystems. Tides are engines of ocean mixing. The global ocean is not a homogeneous body of water. It is a layered system with cold, dense, nutrient-rich water sitting beneath warm, lighter surface water. This layering tends to suppress the mixing of nutrients from the deep into the surface layers, where photosynthetic organisms, algae, phytoplankton, can use them to grow. Tides, particularly where they interact with shallow continental shelves and undersea ridges, create turbulence that breaks down this layering and brings deep nutrients to the surface. Without strong tidal mixing, ocean surface layers in many regions would become more nutrient depleted. Phytoplankton, the microscopic organisms that form the absolute base of nearly all marine food webs and that produce roughly half of all oxygen in Earth's atmosphere, would face a less productive ocean. Fewer phytoplankton means less food for zooplankton. Less food for zooplankton means less food for small fish. And that cascading effect works its way up to every animal that lives in or around the sea. Less oceanic productivity, less atmospheric oxygen generation, a quieter, flatter, less biologically explosive sea. And then there is the climate. The ocean is Earth's climate regulator. It absorbs heat from the tropics and redistributes it toward the poles through a vast, planet-spanning system of currents. This system is driven partly by wind, which itself is driven by solar heating and the Coriolis effect, and partly by differences in water temperature and salinity, a process called thermohaline circulation. Tidal mixing contributes to thermohaline circulation by disrupting the density stratification that would otherwise trap cold, salty water at the ocean floor. Without tidal mixing, the deep ocean could become even more stratified, and the global ocean conveyor belt, which keeps northern Europe warm, which regulates rainfall patterns across entire continents, which stabilizes climate in ways that make agriculture possible, could be weaker or organized differently. Now add to this the effect of axial tilt instability. Remember what we said earlier. Without the moon, Earth's axial tilt would wander chaotically over millions of years. When the tilt is low, the difference between seasons nearly disappears. The tropics remain hot year-round, but the polar regions stop receiving their seasonal burst of warmth. Sea ice expands. Ice sheets grow. When the tilt swings high, the opposite happens. The poles bake in summer and freeze catastrophically in winter, with rapid, extreme swings in ice coverage. These tilt-driven climate swings would interfere with the development of stable, long-term climate patterns. Ice ages might be more frequent, more severe, or might not follow any predictable pattern. The Milankovitch cycles, the astronomically driven rhythms of ice age and interglacial periods, that have paced Earth's climate for millions of years would be profoundly disrupted. A moonless Earth is not just a world without tides. It is a world with a less stable climate, more prone to sudden, extreme shifts, less hospitable to the kind of steady, reliable environmental conditions in which complex ecosystems and, eventually, complex civilizations can take root. Here is where the thought experiment becomes genuinely uncomfortable, because when you start tracing the threads of how the moon has influenced life on Earth, you quickly arrive at a question that has no comfortable answer. Would life even exist here without it? Let's start at the very beginning of life. The most widely accepted theories for how life originated on Earth involve chemistry happening in specialized environments, places where organic molecules could concentrate, react, and build up complexity. Tidal pools and coastal wet-dry cycles have long been considered one of the most promising candidates for this primordial chemistry lab. Here's why. Every time a tidal pool is exposed at low tide, the water evaporates, and the concentration of molecules inside the pool increases dramatically. Then the tide comes back in, diluting and reshuffling the mix. This rhythmic concentration and dilution acts as a natural catalyst for chemical complexity. It drives the formation of polymers, long chains of molecules, in ways that wouldn't happen in a consistently diluted ocean. It tests and filters structures, favoring those that are chemically stable. Some researchers have argued that without strong tidal cycles creating these wet-dry environments, the specific chemical conditions needed to produce self-replicating molecules, the first primitive precursors of life, might never have arisen. If they're right, then removing the moon doesn't just change life on Earth, it removes it entirely. Now, not all origin of life researchers agree. There are other candidate environments, hydrothermal vents on the deep ocean floor, for instance, which operate entirely independently of tidal activity. Life might still have arisen, just later, differently, perhaps less abundantly. But let's say, generously, that life does arise in our moonless Earth, perhaps around those deep-sea vents, perhaps through some other pathway. What happens next? The evolution of life is a story of adaptation to environments, and in a moonless Earth, the key environments are different. The intertidal zone, that extraordinary evolutionary pressure cooker, either doesn't exist or is far less extreme. The organisms that evolved there over hundreds of millions of years, developing extraordinary resilience and biochemical versatility, might not have developed the same capabilities. Some of the evolutionary innovations that came from intertidal evolution might simply not happen. More significantly, consider the transition from sea to land. The colonization of land by life is one of the most important events in the history of complex animals. It happened roughly 375 to 400 million years ago, when certain fish, the ancestors of all land vertebrates, began hauling themselves out of shallow water and surviving in the open air. The first steps, literally and figuratively, onto dry land. These fish, organisms like Tiktaalik, were probably navigating tidal flats and shallow coastal marshes. They were exploring the intertidal zone, the same zone that would be far smaller and less developed in a moonless world. The gradual, millennia-spanning process of learning to breathe air, support their own weight, and navigate exposed land was enabled by the existence of environments where water and land intermix. The intertidal zone was, in a very real sense, the training ground for terrestrial life. It was the zone where organisms first learned to cope with air exposure, to deal with temperature extremes, to develop primitive weight-bearing structures. Without it, the transition to land might never have happened, or it might have happened much later through a different pathway, producing different organisms. And then there is the matter of lunar cycles and biological rhythms. Life on Earth is exquisitely sensitive to light cycles, circadian rhythms, the internal clocks that regulate almost every aspect of metabolism, behavior, and physiology in nearly every living thing are primarily driven by the 2-4-hour light-dark cycle of the Sunday. But lunar cycles run a close second in biological importance. The roughly 29.5-day lunar cycle, the synodic month, has been woven into the biology of an extraordinary number of species. Coral reefs around the world reproduce synchronously on specific nights following a full moon, releasing billions of eggs and sperm into the water simultaneously in one of nature's most spectacular mass events. Sea turtles time their beach arrivals partly according to lunar cycles. Certain insects emerge, mate, and die on lunar schedules. The female reproductive cycles of many mammals, including humans, follow a roughly monthly rhythm that may have been calibrated by millions of years of lunar timekeeping. Certain species of bristleworm, the palolo worm of the South Pacific, swarms for reproduction in a period so precisely timed to the lunar calendar that local people have traditionally used it as a food source and can predict it to the day. Fiddler crabs adjust their foraging behavior to the lunar cycle. Dung beetles use the Milky Way and the Moon as navigational references. The list goes on and on. Strip away the Moon, and you strip away an entire layer of biological timekeeping and behavioral cue that has been integral to the lives of countless species for hundreds of millions of years. Animals that currently synchronize reproduction, migration, feeding, or dormancy to lunar cycles would have to reorganize their biology around something else, or those behaviors might simply not evolve in the first place. The great synchronized reproduction events that drive marine food webs, the predictable explosive abundance that feeds everything from whale sharks to seabirds, might not exist in the same form. The ocean's productivity calendar, already disrupted by the loss of strong tidal mixing, would lose another organizing principle. And the animals that did emerge, they might be unrecognizable to us. Without the moon's steadying influence on Earth's axial tilt, life would have had to adapt to wildly varying climatic conditions over geological time. The evolutionary pressure of a chaotically tilting planet would favor extreme generalists organisms capable of surviving enormous swings in temperature, day length, and season. Specialists, the intricate, perfectly tuned organisms that have evolved to fill specific ecological niches in stable environments, might be much rarer. The extraordinary biodiversity of tropical rainforests, a product of millions of years of stable, warm, wet conditions, might not exist. Complex life might exist in a moonless Earth, but it would be a different complex life, hardier, perhaps, more adaptable, but likely less diverse, less specialized, and potentially far less cognitively sophisticated. Which brings us to the most personal part of this story. Let's say, against all the evolutionary odds we've just described, that somehow, in some form, Something like humans exists in a moonless Earth. Maybe the path was longer, stranger, harder. But here we are, a species with fire, with language, with the capacity to look at the night sky and ask questions about it. What does that civilization look like? The first and most immediate difference is the night itself. Without the moon, there is no source of nighttime illumination beyond the stars and the fire. And unlike moonlight, which varies predictably with the lunar cycle, giving reliable bright nights near the full moon, the stars provide a constant but dim backdrop that illuminates almost nothing at ground level. This is not a trivial difference. For most of human prehistory and history, darkness was not just an inconvenience. It was a danger. Nocturnal predators, lions, leopards, hyenas, used darkness to their advantage. Traveling at night without moonlight was genuinely life-threatening in environments where large predators were present. The rhythm of human activity was partly organized around the predictable availability of moonlight. Hunter-gatherer societies around the world have been observed to extend hunting and social activities on clear, full moon nights. Archaeological evidence suggests that some of the most significant social gatherings and rituals in early human communities were timed around bright lunar periods when large groups could move and interact safely in the open at night. Without the moon, the night is simply and absolutely dark when there is no fire. Human, social, and economic life would be more constrained by darkness. Settlements might have developed differently, more compact, more defensive, organized around reliable fire-making rather than exploiting the freedom that moonlit nights provided. But perhaps the most profound effect of a moonless sky on human civilization is calendar. Almost every ancient civilization independently developed a lunar calendar before developing a solar one, and it's not hard to see why. The moon is the most obvious, most dramatic, most reliably changing object in the night sky. Its phases follow a cycle precise enough to count a new moon, a waxing crescent, a half moon, a waxing gibbous, a full moon, and back again in 29.5 days. It is nature's most intuitive counting device. The concept of a month is lunar. The word itself, in almost every Indo-European language, derives from the word for moon. In English, month, moon, from the Proto-Germanic menoth, moon. In Latin, mensis, for month, comes from mene, moon. In Arabic, the word for moon and month are the same root. The Gregorian calendar still observes a rough lunar rhythm in its 30-day months, even though it has been decoupled from the actual lunar cycle. Calendars were among the first technologies of civilization. The ability to predict the seasons, to know when to plant, when to harvest, when the floods come, when the dry season begins, was foundational to settled agriculture and therefore to everything that agriculture made possible: cities, specialization, writing, law, government. Ancient Babylonian astronomy was fundamentally lunar astronomy. The Babylonians developed some of history's most sophisticated mathematical methods in the service of predicting the moon's movements and cycles. The ancient Egyptian calendar, though ultimately solar, was synchronized and checked against the lunar cycle. The Jewish, Islamic, Hindu, and Chinese calendars are all lunar or lunisolar. They use the moon as their primary timekeeping mechanism. Without the moon, humans would still have needed calendars. The sun itself provides a cycle. The year and various solar phenomena like solstices and equinoxes can be tracked with surprisingly simple instruments. But the development of astronomical sophistication might have taken a different path. The intricate system of number symbolism, myth, and mathematical prediction that grew up around the lunar cycle in so many cultures would simply not exist. Religion, too, would be fundamentally different. The moon is one of the most universally worshipped objects in the history of human religion. From the Sumerian moon god Nanasuen to the Egyptian Khonsu, from the Greek Selene to the Roman Diana, from the Hindu Chandra to the Aztec Metzli, virtually every ancient culture developed elaborate mythology around the moon. The moon was associated with the feminine, with fertility, with the passage of time, with death and rebirth. These are not arbitrary cultural choices. They reflect deep human responses to the moon's observable behavior, its monthly death and rebirth in the sky, its influence on tidal rhythms and possibly on human reproductive cycles, its dramatic transformation from a thin silver crescent to a blazing full orb and back again. These were experiences that demanded explanation, and the explanations became the core of myth, ritual, and theology. Without the moon, these religious traditions simply do not exist. The specific shape of human spirituality, the lunar goddess traditions, the calendar-based festivals, the tidal and fertility symbolism is absent. Human religion develops from other sources: solar worship, the stars, natural forces. Perhaps the cosmos feels less personal without that luminous, shape-shifting, reliably returning companion in the sky. And then there is navigation. The moon was a navigational reference long before modern astronomy. Polynesian navigators used the moon, along with stars and ocean swells, to cross thousands of miles of open Pacific. Arabian sailors used the moon's position to navigate the Indian Ocean. Even the simple understanding of compass direction from the moon's phase and position, rising approximately in the east, setting approximately in the west, higher in the south in the northern hemisphere, was practical knowledge used by travelers across the ancient world. Celestial navigation without the moon is harder, more reliant on the more complex patterns of the stars. It might have slowed the rate at which human explorers crossed open water. The peopling of the Pacific, which required extraordinary navigational skill, might have happened later or not at all. The great seafaring civilizations, Polynesia, the Phoenicians, the Vikings, the Arabs, might have had different trajectories, different limitations, different worlds to discover. Perhaps most intriguingly, the moon was the inspiration for the first great scientific revolution. It was the moon that forced Galileo to take his telescope seriously as a scientific instrument, because what he saw through it, mountains, craters, a surface unmistakably Earth-like, shattered the Aristotelian doctrine that celestial bodies were perfect, unchanging spheres. It was the moon's orbit that Newton used to test and validate his theory of universal gravitation. The moon was, in a very real sense, the object that turned physics from natural philosophy into mathematical science. Without the moon, the specific trigger for the scientific revolution might not have existed in the same form. Other discoveries might have played the same role eventually, but the moon was particularly useful because it is close enough to be observed in detail, large enough to see surface features with a simple telescope, and its orbital mechanics are complex enough to reward mathematical analysis. A civilization without a moon is not necessarily a civilization without science, but it might be a civilization that arrived at mathematical physics later, via a different route and with a different flavor. We've been talking mostly about what a moonless Earth would look like over the timescales of biology and civilization, millions of years, thousands of years, centuries. But the consequences of having no moon extend into the deep future, billions of years from now. And some of those consequences are stranger and more far-reaching than anything we've discussed so far. Let's start with that axial tilt problem, which we've mentioned several times but haven't fully explored in terms of its long-term consequences. Without the moon's gravitational stabilization, Earth's axial tilt would undergo a chaotic random walk over millions to hundreds of millions of years. Computer simulations of this process, based on models of the gravitational interactions between Earth and the other planets, particularly Venus, which provides the strongest perturbing influence, suggests that a moonless Earth's axial tilt could range from nearly 0 degrees to perhaps 85 degrees or more. These are not gentle fluctuations. They are civilization-ending, mass extinction-driving swings in global climate. Earth's axial tilt swinging dramatically in a simulation at near zero tilt, the tropics bake and the poles are locked in mild, seasonless cold. At high tilt, the poles are alternately scorched and frozen, and the tropics experience dramatic seasonality they don't currently have. At zero axial tilt, Earth has no seasons. The tropics receive the same intense year-round sunlight they always have, but the higher latitudes, instead of receiving a burst of summer warmth that melts winter ice, remain cold year-round. Ice sheets spread. With enough ice, the reflectivity of Earth's surface increases, cooling the planet further. You can, in principle, trigger a runaway glaciation, a snowball Earth event in which the entire planet freezes over because the summer sun is never strong enough at high latitudes to melt the ice that builds up during the cold season. Earth has actually experienced snowball Earth events before, perhaps 2 or 3 times in its history, most recently around 700 million years ago. They are among the most extreme climate events in Earth's history. The planet becomes almost entirely covered in ice and snow. Global temperatures plunge to perhaps -50 degrees Celsius on average, and life is confined to tiny refugia, volcanic islands, hydrothermal vents, and equatorial regions where geothermal activity keeps a little liquid water available. Recovery from a snowball Earth requires millions of years of volcanic CO2 buildup to warm the planet enough to melt the ice. Complex life, if it survives at all, is set back enormously. In a moonless world, snowball Earth events might be more frequent, triggered by the drift of axial tilt toward low values. Life would be repeatedly hammered back toward simplicity. The planet slowly freezing white ice creeping down from the poles over centuries and millennia, the blue oceans narrowing toward the equator, until finally the last liquid water disappears and the whole world is white. On the opposite end, a high-tilt Earth faces its own catastrophe. At 60 or 70 degrees of tilt, the poles point almost directly at the sun during summer and almost directly away during winter. The polar regions would experience months of continuous sunlight heating, followed by months of utter darkness and extreme cold. Ice sheets might melt completely in summer and then reform catastrophically in winter. The global ocean circulation would be radically disrupted. Weather systems, forced to manage extreme thermal contrasts, would be violent beyond anything in our geological record. The effect on evolution would be dramatic. The organisms capable of surviving in this environment would have to be extraordinarily robust and adaptable. Life would likely persist. It has survived snowball Earths and mass extinctions before, but its complexity and diversity would be repeatedly set back. There is a scientific concept, sometimes called the rare Earth hypothesis, the idea that the specific suite of conditions needed for complex life to evolve and persist are extraordinarily rare in the cosmos. The moon's existence, according to some versions of this hypothesis, is one of those conditions. A large moon that stabilizes axial tilt and moderates tidal environments might be a prerequisite for the development of the kind of stable, long-term biosphere in which intelligence can evolve. If the rare Earth hypothesis is correct, then moonless Earths in other star systems, and there must be billions of them, are worlds of simpler life, if life at all. Worlds of bacteria and algae, and perhaps some invertebrates, cycling through climatic catastrophes before complex nervous systems can evolve. And then there is the long-term question of Earth-Moon dynamics themselves. In our actual timeline, the Moon is slowly receding from Earth. In about 600 million years, the Moon will be far enough away that total solar eclipses, in which the Moon perfectly covers the Sun, will no longer be possible. The Moon will appear too small in the sky to cover the solar disk. That particular cosmic coincidence, which has struck awe into human beings for our entire existence as a species and driven enormous scientific discovery, will end. In perhaps 5 billion years, as the Sun expands into a red giant, both Earth and the Moon face incineration. But in a moonless world, Earth arrives at that endpoint differently, possibly with less complex life, possibly without any intelligent observers to witness or mourn it. The Moon has not just shaped Earth. It has given Earth times, geological, evolutionary, civilizational time, by keeping conditions stable enough for complexity to build, slowly but surely, across billions of years. Without it, the window for complexity may have been shorter, more interrupted, more easily closed. But here is the thing worth remembering, the thing that puts all of this in perspective. The Moon we take for granted. Dawn over a moonlit landscape. The Moon still visible in the pale morning sky, fading as the sun rises. A beach with gentle surf, the product of lunar tides. A forest edge where the shadows are deep and life is dense. The Moon formed from a catastrophe. A world-ending collision, a planetary destruction, a chaos so total that it vaporized continents and boiled oceans. Out of that destruction came something unexpected, a companion, a stabilizer, a tide maker, and a timekeeper, and a nightlight for 1 billion years of evolution. We look at the Moon and we see a dead rock, craters and dust and silence. But what we should see, what this entire thought experiment asks us to see, is a silent architect. Without the Moon, the tides that sculpted our coastlines and drove the chemistry of life's origin might never have existed. or might have been too weak to do their work. The stable climate that allowed complex ecosystems to develop over hundreds of millions of years might have been shredded by a wobbling, drifting axial tilt. The intertidal zone, that evolutionary pressure cooker where life first learned to leave the sea, might have been too narrow and calm to serve as the cradle it became. Without the moon, the nights would have been darker, the days would have been shorter and more frantic, the storms would have been fiercer, the seas would have been quieter but more nutrient poor. The fish that learned to walk onto land might never have had the exposed tidal flats to practice on. Without the moon, there might have been no monthly calendar, no lunar goddess traditions, no navigational reference for the great ocean crossings, no perfect celestial object to inspire the mathematical physics that became modern science. And there might have been no us. A person standing on a beach at night, looking up at the full moon, the reflection stretching across the water toward them, the quiet sound of waves. There is something humbling about this realization that goes beyond science. We did not earn the moon. We did not choose it. It arrived through random violence, an accident of the solar system's chaotic adolescence, a fortunate coincidence of timing and orbital mechanics that placed a Mars-sized object in our path at just the right moment and at just the right angle to leave behind exactly the right-sized companion. We live in the gravitational shadow of a lucky accident. And that moon, that ancient, gray, scarred, endlessly patient moon, has been working on our behalf ever since, steadying our tilt, stretching our days, pulling our oceans in and out, providing our months, lighting our nights, inspiring our myths, grounding our science, shaping our biology in ways we are still cataloging, still discovering, still failing to fully appreciate. The next time you see the moon, a crescent in the western sky after sunset, or a gibbous rising over the eastern hills, or a full, blazing disk hanging impossibly large and bright near the horizon, try to hold this in your mind for just a moment. You are looking at the reason the world is what it is. You are looking at a 4-5 billion year old accident that decided to become something indispensable. You are looking at the sculptor of tides, the stabilizer of seasons, the timekeeper of ancient calendars, and the quiet guarantor of your own existence. And it is just hanging there, 384,000 kilometers away, doing its job, asking for nothing. Final slow pullback from the moon's surface. The Earth, visible in the lunar sky, blue, white, impossibly beautiful. The camera continues to pull back until both Earth and Moon are small in the darkness, then smaller, then lost among the stars. Maybe it's time we noticed. That's it for today. If this journey through a moonless Earth moved you, or even just made you look up tonight, hit that like button. It genuinely means a lot, and it helps this channel reach people who love exploring these big questions. Subscribe if you haven't already, because next time we're asking another question that will turn your understanding of the solar system inside out. You don't want to miss it. And leave a comment below. What surprised you most? What part of this story hit hardest? I read every single one. Until next time, keep looking up.